Welcome to our quantum deep dive. Today we're plunging into a field that's, well, it's really reshaping our fundamental understanding of computation. Quantum complexity theory. And this isn't just about building faster computers, it's more about exploring how quantum mechanics might push the very limits of what's possible and how quickly we can get answers. Our insights today come from a really fantastic essay by Jürgen Schneppat titled Quantum Komplexitätstheorie, Berechnung neu definiert.
Yeah, it's a great piece. What's truly fascinating here, I think, is how this field sits right at the crossroads. It bridges theoretical computer science and quantum physics, and it asks these profound questions about what problems are genuinely solvable and, by what means.
Right.
It raises a critical question for all of us, really. Can quantum mechanics truly break through the limits, the really tough limits of classical computers?
Or are there boundaries even for these quantum machines?
Exactly. Are there fundamental boundaries even here? At its heart, quantum complexity theory looks at the resources, think time, think memory needed to solve problems on a quantum computer. And it does this by leveraging those, well, frankly, mind-bending quantum principles. Superposition, entanglement, and interference.
That's a powerful start. So let's dive into the mechanics a bit. If we boil it down, what does quantum complexity theory actually mean? What are its main goals?
Okay, so quantum complexity theory is a specialized area within theoretical computer science. Its main job, its focus, is on understanding the inherent difficulty, how hard problems are specifically for a quantum computer. It investigates how these unique quantum rules impact computational complexity.
So it's asking different questions than classical theory.
In a way, yes. It's grappling with key questions like, which problems can a quantum computer solve efficiently really fast that are just intractable for classical ones? How do these new quantum complexity classes, these categories of problems, fit into the picture we already have, the classical hierarchy? And ultimately, are there fundamental limits, even to quantum computing power itself? A really central concept here is a complexity class called BQP. That stands for Bounded Error Quantum Polynomial Time.
BQP.
Yeah, BQP. This class basically includes all the problems that a quantum computer can solve with a high probability of being right specifically. You need at least a 2/3 chance, and it has to do it in a reasonable polynomial amount of time. It's crucial to remember, though, quantum algorithms are probabilistic by nature. They don't always give the right answer every single time.
But they get it right most of the time, with high confidence.
Exactly. Very high confidence, like that 2/3 threshold or better. So what does this all mean for you, the listener?
Well, it's really about understanding the ultimate power, but also the inherent limitations of these revolutionary machines and, figuring out how they might finally crack problems we currently just can't solve efficiently.
The implications here sound huge. For both computer science theory and for physics itself. Can you give us the high-level view on that?
Absolutely. They're pretty transformative. From the computer science perspective, quantum complexity theory just opens up entirely new avenues for speeding up computations.
Yeah.
Think about algorithms like Shor's algorithm.
For factoring, right? The one that scares cryptographers. That's the one. Or Grover's algorithm for searching databases much faster. These offer either exponential or, in Grover's case, quadratic speedups over the best classical methods we know. It also helps define new problem categories like BQP, which we mentioned, but also others like QMA and QIP. These are essential tools for analyzing quantum computer performance. And a huge open question, a real frontier for computer scientists, is whether BQP truly goes beyond classical capabilities. Does it maybe even include problems we currently think are NP hard? That's a big one.
Wow, okay. And on the physics side?
Well, the consequences are equally profound there. You have Richard Feynman, way back in 1982.
A famous lecture, yeah.
Right. He famously proposed that quantum computers would be uniquely suited, exceptionally efficient at simulating complex quantum systems. And this is incredibly important for fields like chemistry, materials science, designing new drugs. Anywhere, understanding quantum interactions is key. Plus, studying quantum complexity actually helps us understand information processing at the quantum level better. It even contributes to how we interpret quantum mechanics itself. And of course, all this theoretical advance has direct practical impacts. It's driving innovation in cryptography, as we said, but also in optimization machine learning.
Okay, before we get too deep into the quantum side, maybe we should quickly ground ourselves. To really appreciate this quantum leap, what was the picture before quantum entered the scene? What were the key classical ideas?
That's a great point. Yeah, a quick refresher on classical complexity theory is useful. It really got going in the 1960s, building on work by giants like Alan Turing, von Neumann, Stephen Cook, and it's all about classifying problems based on how hard they are for a standard classical computer, usually measured in time and memory needed.
Like P and NP, those are the big ones you hear about.
Exactly. P stands for polynomial time. These are the problems considered easy or efficiently solvable by a classical computer. Think sorting a list or finding the shortest path on a map. Then there's NP, non-deterministic polynomial time. Now, these are problems where if someone gives you a potential solution, you can check if it's correct really quickly in polynomial time.
But finding the solution in the first place is hard.
That's the crux of it. Finding the solution might be incredibly hard. Think about cracking complex codes or finding the optimal solution to a massive logistics problem, like the traveling salesperson problem. Verifying a proposed route is easy. Finding the best route is potentially very, very hard.
And the big question is whether P equals NP.
That's the $1 million, actually, it's a Clay Mathematics Institute Millennium Prize problem, so technically a $1 million question. Can every problem whose solution can be verified quickly also be solved quickly? Most computer scientists strongly suspect P does not equal NP. They believe there's a whole class of problems that are fundamentally hard for classical computers.
And there are other classes too, right? Like PS space.
Right. PS space includes problems solvable using a polynomial amount of memory, even if it takes exponential time. We know the hierarchy generally goes. P is inside NP, which is inside PS space. And we know for sure that P is different from x of P time exponential time. So this whole classical framework PNP, PS space, is vital context. Because quantum complexity theory builds directly on it. It asks, where does quantum power fit in? Does it let us solve NP problems efficiently? Does it go beyond NP? Where does BQP sit relative to PS space?
Okay, that classical picture helps a lot. So how did we actually make the jump from those classical ideas to thinking, hey, maybe quantum mechanics can do something fundamentally different? What were the first sparks?
Well, the very first concepts of quantum information started bubbling up, as we mentioned, with Richard Feynman in '82. His insight was key. Classical computers struggled to simulate quantum systems because, well, quantum systems are quantum. He argued you'd need a computer that operates on quantum principles to simulate them efficiently.
A quantum computer for quantum problems.
Makes sense. It does. Then, in 1985, David Deutsch took a huge step. He formalized the idea, creating a theoretical model of a quantum computer, the quantum Turing machine. And Deutsch showed, theoretically at least, that this quantum machine could potentially outperform classical computers on certain tasks. That was a big moment.
But the real explosion came later, in the 90s.
Exactly. The 1990s were when quantum complexity theory really took off. You had Peter Shor in 1994 dropping his bombshell algorithm for factoring large numbers in polynomial time. That sent shockwaves through the cryptography world because so much relies on factoring being hard.
Right. Suddenly, RSA encryption looked vulnerable, at least theoretically.
Theoretically, yes. And then, just 2 years later, 1996, Grover came up with his search algorithm. It didn't offer an exponential speedup like Shor's, but a quadratic one. Still, a massive improvement for searching large, unstructured data sets. These early breakthroughs were crucial. They showed very clearly that quantum computers weren't just slightly faster classical machines. They operated on fundamentally different rules, opening up completely new computational possibilities.
Okay, let's dive into that core magic then. We talk about bits being 0 or 1. What exactly is a qubit? And what are these quantum principles, superposition, entanglement, interference, that give quantum computers their power?
Right, the qubit. It's the fundamental unit of quantum information, analogous to the classical bit. But here's the key difference. A classical bit is either 0 or 1. A qubit, however, can be 0. It can be 1. Or, and this is crucial, it can be in a superposition of both states at the same time.
Both 0 and 1 simultaneously. How does that even work?
Think of it like a spinning coin before it lands. It's neither heads nor tails, but a combination of both possibilities. Mathematically, we represent it as a combination, like alpha times state 0 plus beta times state 1, where alpha and beta tell you the probabilities of getting 0 or 1 if you measure it. This ability to hold multiple values at once is what allows quantum computers to explore many possibilities in parallel.
Okay, superposition lets one qubit hold more information. What else is in the quantum toolkit? You mentioned entanglement.
Entanglement. This is maybe the strangest, most non-intuitive part. You can link two or more qubits together in a special way. Their fates become intertwined. No matter how far apart you separate them across the room or across the galaxy, if you measure the state of one qubit, you instantly know the state of the other entangled qubit. Their states are correlated in a way that classical physics just can't explain.
Like Einstein's spooky action at a distance.
Exactly that. It's a fundamental resource for quantum communication protocols like quantum teleportation, and it's also vital for many quantum algorithms. It creates correlations stronger than anything classical.
Wow. Okay, superposition, entanglement. And the third one was interference.
Yes, quantum interference. Just like waves, light waves or water waves can interfere, adding up constructively, getting bigger, or destructively canceling out, the probability amplitudes associated with quantum states can do the same. Quantum algorithms are cleverly designed to use interference. You set things up so that the paths leading to the wrong answers cancel each other out, while the paths leading to the correct answer reinforce each other.
So you amplify the signal for the right answer.
Precisely. You harness interference to make the probability of measuring the correct solution much, much higher. Think of Grover's search algorithm. It uses interference to amplify the state corresponding to the item you're searching for. So these three, superposition, entanglement, and interference, aren't just physics curiosities. They're the active ingredients, the building blocks for this entirely new way of computing.
And how do we actually control these qubits and make them do things? Are there quantum versions of logic gates?
Absolutely. Just like classical computers use gates like A and D or not T, quantum computers use quantum gates to manipulate qubits. These gates are essentially carefully controlled physical operations. For instance, the Hadamard gate, H, is famous for putting a qubit into an equal superposition of 0 and 1. Then you have Pauli gates, XYZ, that perform rotations, kind of like bit flips or phase shifts. And crucially, you have multi-qubit gates, like the CNOT gate, controlled not D.
What does CNOT do?
CNOT acts on two qubits. It flips the state of the second qubit only if the first qubit is in the state 1. It's fundamental for creating entanglement between qubits, linking their fates together. These gates form a universal set, meaning you can combine them to perform any possible quantum computation, just like classical gates can build any classical computation.
Okay, so we have the qubits and the gates to manipulate them using superposition, entanglement, and interference. Now let's connect that back to those game-changing algorithms.
Yeah.
Shor's algorithm for factorization. Why exactly is it such a big deal for security?
Right, Shor's algorithm. Its power lies in tackling the problem of finding the prime factors of a large integer, n. Let's say n equals p times q, where p and q are large prime numbers. Finding p and q, if you only know n, is believed to be incredibly hard for classical computers. The best-known classical algorithms take time that grows exponentially with the number of digits in n.
And that hardness is the foundation of RSA encryption, right?
Exactly. RSA security relies directly on the difficulty of factoring large numbers, but Shor's algorithm changes the game completely. It uses quantum principles, particularly something called the quantum Fourier transform, which is incredibly good at finding periodic patterns hidden within functions to find those prime factors p and q in polynomial time. The time it takes grows only slowly, like a power of the number of digits in n.
So exponential difficulty becomes polynomial difficulty.
Precisely. A task that might take a classical supercomputer billions of years suddenly becomes feasible, maybe taking hours or days on a sufficiently powerful quantum computer. That's why it's such a threat. It means that RSA encryption and similar systems like Diffie-Hellman and elliptic curve cryptography, ECC, could potentially be broken, rendering much of our secure online communication, banking, and data storage vulnerable.
That really drives home the impact. Okay, what about Grover's algorithm? You said it's for search. How does that work, and where is it useful?
Grover's algorithm tackles a different kind of problem: searching an unsorted database. Imagine you have a huge list of n items, and you're looking for one specific item, say, finding a specific phone number in an unsorted directory. Classically, on average, you'd expect to check about half the items, n2. And in the worst case, you might have to check all n items. The time scales linearly with n.
Makes sense. You just have to look through them.
Right. But Grover's algorithm uses quantum superposition and interference in a clever way. It essentially puts the system into a superposition of all possible items, and then iteratively applies an operation that amplifies the amplitude of the state corresponding to the item you're looking for, while diminishing the others. The result is that it can find the target item in roughly the square root of n steps.
Square root of n. So not exponential like Shor's, but still faster.
Exactly. It's a quadratic speedup. If you have 1,000,000 items in 106, Classically, you might need up to 1,000,000 checks. Grover's needs only about the square root of 1,000,000, which is just 1,000 checks. That's a huge difference. While not world-breaking like Shor's for cryptography, this quadratic speedup is still incredibly powerful for many problems that involve searching or exhaustive checking, like certain optimization problems or finding collisions in cryptographic hash functions. It makes many computationally intensive tasks significantly more tractable.
The theory is definitely compelling, maybe even a bit scary for security. But let's talk practicalities. Where are we actually with building these machines? We hear headlines, but are they ready for prime time? What are the big roadblocks?
That's the crucial question, isn't it? It's where the incredible theoretical potential meets some really tough engineering reality. An ideal quantum computer needs lots of qubits. They need to be controllable, stable, connected, and crucially, almost error-free.
And the reality?
The reality is, well, we're not there yet. Not even close for the big, impactful applications like breaking RSA. There are various physical systems being explored, superconducting circuits like Google and IBM use, trapped ions, photonic qubits, spin qubits. Each has its own pros and cons regarding stability, error rates, scalability. But the core challenges are universal and immense. First, decoherence. Quantum states are incredibly fragile. Any interaction with the environment, heat, vibration, stray electromagnetic fields can destroy the delicate superposition and entanglement. Keeping qubits coherent long enough to compute is a massive hurdle.
Like trying to keep a soap bubble intact in a hurricane.
That's a pretty good analogy. Then there's the challenge of controlling large numbers of qubits. As you add more qubits, controlling them precisely and performing gates accurately becomes exponentially harder. And you need efficient inter-qubit connections. Performing multi-qubit gates like CNOT requires strong, reliable coupling between qubits, which gets tricky to engineer at scale. Right now, state-of-the-art systems have maybe 50 to a few hundred physical qubits. But the algorithms, like Shor's, for breaking real-world encryption, likely need millions of highly reliable, error-corrected logical qubits. We're orders of magnitude away.
Millions, wow. And you mentioned errors. Given how fragile these states are, how do you deal with computations going wrong? Error correction sounds essential, but maybe impossible.
It's absolutely essential and incredibly challenging. Quantum computations are inherently noisy. Errors creep in from imperfect gates, decoherence, faulty measurements, and you hit on a key difficulty. The no-cloning theorem in quantum mechanics says you can't simply copy an unknown quantum state. So the classical trick of making copies and comparing them to detect errors doesn't work.
So how do you correct errors then?
The solution lies in quantum error correction codes, QECCs. Think of codes like the Shor code, the Steen code, or surface codes. The basic idea is redundancy, but in a very clever quantum way. You encode the information of one perfect logical qubit across many physical qubits, maybe dozens, hundreds, or even thousands. These physical qubits are entangled in a specific pattern. By making collective measurements on subsets of these physical qubits without disturbing the encoded logical state, you can detect if an error occurred on one of them, and importantly, what kind of error it was, like a bit flip or a phase flip, and where it happened. Then you can apply a correction.
That sounds incredibly complex. Does it actually work?
Theoretically, yes, and experimentally, people are making progress demonstrating the basic principles. But the catch is that these codes only work if the error rate of the underlying physical qubits and gates is already very low, below a certain threshold, often estimated around 10.3 to 10.4 or less than 1 error per 1,000 or 10,000 operations. Achieving that level of fidelity consistently across many qubits is still a major engineering frontier.
So where does that leave the big players like IBM, Google, D-Wave? What's their status?
Well, they're all pushing hard. IBM Quantum is a leader in superconducting qubits. They have chips like the Eagle with 127 qubits and a roadmap aiming for over 1,000 qubits and demonstrating basic error correction relatively soon. Google Quantum AI also uses superconducting qubits. They achieved that famous quantum supremacy claim in 2019 with their 53-qubit Sycamore processor.
Right, the supremacy claim. Remind us that generated some debate, didn't it? What was the upshot?
It did. Google claimed Sycamore performed a specific, highly contrived task sampling the output of a random quantum circuit in about 200 seconds, a task they estimated would take the world's most powerful classical supercomputer, at the time IBM Summit, about 10,000 years. IBM pushed back, arguing that with better classical algorithms and more storage, Summit could actually do it in maybe 2.5 days, not 10,000 years. Still much slower than Sycamore, but not insurmountably so. The key takeaway wasn't that quantum computers were suddenly useful for real problems, but that they had reached a point where they could, provably, do something, even if artificial, faster than any known classical method. It was a milestone, but practical utility is still further off.
And D-Wave.
Yeah,
They seem different.
they are. D-Wave Systems focuses on a different approach called quantum annealing. Their machines have thousands of qubits, up to 5,000 or more, but quantum annealers aren't universal quantum computers capable of running Shor's algorithm. They are specialized hardware designed to find the minimum energy state of a particular quantum system, which maps well onto certain types of optimization problems. They've shown promise for specific applications, but it's not the same as the gate-based universal quantum computers IBM and Google are building. So, yeah, lots of progress, lots of excitement, but the really hard engineering challenges for fault-tolerant, large-scale quantum computing are still very much ahead of us.
We've looked at the past and the challenging present. Let's gaze into the crystal ball, or maybe just the whiteboard. What are the big unknowns, the really deep questions that quantum complexity theorists are wrestling with right now?
Oh, there are some fundamental ones. A huge one is pinpointing the exact power of BQP, that main quantum complexity class relative to the classical classes. We know P is inside BQP and BQP is inside PS space, but the big open questions remain. Is NP also inside BQP? Could quantum computers efficiently solve all problems whose solutions are easy to check? Most people suspect not, but we don't know.
So we don't know if quantum computers can crack all NP problems efficiently.
But we don't. Shor's algorithm tackles factoring, which is thought to be hard classically, but isn't proven to be NP-complete. Finding an efficient quantum algorithm for a known NP-complete problem, like satisfiability, would be monumental. It would imply NP is contained in BQP. Another big question is the relationship between BQP and PS space. Could it be that BQP actually equals PS space, meaning anything solvable with polynomial memory is also solvable efficiently by a quantum computer? Again, we don't know. The current belief is likely BQP is somewhere between P and PS space, possibly incomparable with NP, but it's still uncharted territory.
Any other major theoretical puzzles?
Yes, researchers are exploring quantum analogs of NP-complete problems. Is there a class of quantumly hard problems within BQP? What about classes like QMA, Quantum Merlin-Arthur, which is the quantum version of NP? How powerful is it really? And then there's the intensely practical but theoretically deep question of efficient fault tolerance. Can we build scalable, error-corrected quantum computers without needing an absolutely enormous overhead of physical qubits for each logical qubit? Finding more efficient error-correcting codes is critical. Answering these questions isn't just academic. It fundamentally defines what quantum computers will ultimately be capable of.
Looking forward then, say over the next decade or two, what potential breakthroughs might we realistically see, both in the theory and the hardware? And looping back to security, what does this all mean for the future of cryptography?
Okay, potential breakthroughs. On the hardware side, besides just scaling up current technologies like superconducting qubits and ion traps, there's hope for new types of qubits, like topological qubits, which Microsoft and others are pursuing. These are theoretically much more resistant to local errors, potentially making fault tolerance easier. We'll likely see continued progress towards demonstrating fault tolerance, maybe the first stable, long-lived logical qubits encoded in physical qubits. The major players are aiming for systems with thousands and eventually millions of physical qubits within, say, 10-15 years, enabling more complex simulations and perhaps tackling problems just beyond classical reach. On the theory side, the search is always on for new, impactful quantum algorithms. Beyond Shor and Grover, areas like quantum machine learning are very active, looking for quantum speedups in data analysis and AI. And a deeper understanding of those quantum complexity classes like QMA, QIP, quantum interactive proofs, pinning down their exact power is a key goal.
And the security implications. That seems like the most immediate societal impact.
Absolutely. The threat is real, even if distant. If, or perhaps when, large-scale, fault-tolerant quantum computers become available, current public key cryptography standards like RSA and ECC are broken, completely insecure. This necessitates a global transition to post-quantum cryptography, PQC. These are new cryptographic algorithms designed to be secure against both classical and quantum computers. Standardization bodies like NIST in the US are already well underway in selecting and standardizing these new PQC algorithms, like lattice-based or code-based cryptography.
So the race is on to upgrade our security before the quantum threat materializes.
Precisely. It's a proactive defense measure. We need to deploy these PQC systems widely before a powerful quantum computer exists that could retroactively decrypt stored sensitive information. And interestingly, quantum mechanics also offers a potential solution for secure communication. Quantum cryptography, specifically quantum key distribution, QKD. QKD protocols allow two parties to establish a secret key in a way that any attempt by an eavesdropper to listen in inevitably disturbs the quantum states, thus revealing their presence.
So quantum is both the potential threat and part of the potential solution.
In a sense, yes. QKD offers provable security based on the laws of physics, but it has its own practical challenges for long-distance implementation. The main focus right now for protecting data is developing and deploying classical QQC algorithms resistant to quantum attack. So, yeah, the coming decades will be fascinating. We'll see this interplay between building the quantum machines, understanding their theoretical limits, and developing the cryptographic defenses needed for the quantum era. Your online safety, national security, scientific discovery, they all hang in the balance.
What a journey. We've gone from classical limits through the quantum weirdness of qubits and entanglement to world-shaking algorithms like Shor's, the immense challenges of building these machines, and the deep theoretical questions still driving the field. It really is mind-bending stuff.
It truly is, and I think if we connect this back to the bigger picture, it's clear that quantum complexity theory isn't just about faster calculations or breaking codes, as important as those are. It's really about fundamentally reshaping how we think about information itself, about computation, and maybe even about the physical laws of the universe that permit such computation. It's a field that constantly forces us to challenge our assumptions about what's ultimately possible.
That's a fantastic final thought. It really underscores the depth of this field. We really hope this deep dive into Yurgo Schneppet's insightful work has given you, our listeners, a clearer picture of this revolutionary and sometimes confusing field. If you're eager to explore further, we definitely encourage you to visit schneppet.de. That's schneppet.de for more of Yurgo Schneppet's fascinating insights. Thank you so much for joining us on this quantum deep dive. Until next time, keep exploring.